Okay, good evening, everyone. I'd like to welcome you here this evening to our Speaking of Engineering lecture. My name is Greg Naderer. I'm the Dean of the Faculty of Engineering and Applied Science, and it's a pleasure for me to welcome you here this evening. So I'd like to extend special greetings to our guest speaker for the evening, Dr. Joe DeRaio, on my immediate right, who is an assistant professor in civil engineering. I would also like to acknowledge Jeff Emberley, who is the CEO and Registrar of Paganel to my left. That's professional engineers and geoscientists of Newfoundland and Labrador. Jeff will come up later to speak about Paganel and its sponsorship of this lecture series. So this session is co-sponsored by Paganel, which is an organization with the mandate of regulating engineering and geoscience professions in the public interest in the province of Newfoundland and Labrador, and it has approximately 4,000 members. We are grateful to Paganel for their support of this lecture series. Just a few housekeeping items before we go into tonight's lecture. In the case of an emergency, we should exit this room calmly through the back doors, exit to the right, and through the main exit through the foyer doors of this building on the second floor. Then turn right and cross the street over to the business parking lot, muster station number 22 in the business parking lot as we exit. Also, there are washrooms to the immediate left as you leave this room. This lecture series raises awareness of engineering issues among students and within our community. We are very proud of the work that we do here in the Faculty of Engineering and Applied Science and the accomplishments of our students. I'd just like to briefly tell you a little bit about a recent study that was done at the University of Ottawa. This was done last year, and it involved 14 universities across Canada, including many of the top engineering schools in the country, like Memorial, Waterloo, Queen's, and others. And the study tracked graduates over a 6-year period after they graduated from university. And what the study found is that our Memorial engineering graduates, on average, are paid about $10,000 per year more in salary than graduates of the other engineering schools across the country. And not only are they paid significantly higher than average, they also, the salary gap over other engineering graduates increases to about $12,000 per year after 4 years. So, showing that our students are in higher demand than other programs across the country, and they progress faster through their careers. So we're very proud of that, and no doubt in large part due to our superb co-op programs. So moving on to tonight's lecture, and enough about bragging about our faculty. Tonight's lecture is about how resilient infrastructure can address climate change impact on Newfoundland and Labrador communities. As we know, the impact of climate change is being felt across the province through increased coastal erosion, increased occurrence of extreme precipitation events, such as Hurricane Igor in 2010 and the remnants of Hurricane Matthew in 2016. Tonight, Dr. DeRaio will discuss projected impacts of climate change on our province, how it may impact the drainage infrastructure that we have, the building design, the transportation, and what the provincial government and Memorial Engineering are doing to help protect communities in the future. Dr. DeRaio earned his PhD degree in Civil and Environmental Engineering from the University of Iowa in 2009. He also received a bachelor's in biology at the State University of New York and master's degrees in biology, philosophy, and environmental engineering. Quite a diversified educational background. His research interests include impacts of climate change on stormwater infrastructure, and also he has interdisciplinary research interests that link hydrology, hydraulics, and ecology. Prior to Memorial, he was an assistant professor of water resources engineering at Rowan University in New Jersey and where he worked on the impacts of climate change on local water resources. After receiving his PhD, he worked as a postdoctoral researcher at North Carolina State University, where he developed new models that simulate the effects of land use change and climate change on watershed hydrology and in-stream temperatures that assess the potential long-term effects on aquatic organisms. Dr. Darayo is a member of Paganel. Please join me in welcoming him this evening and inviting him to speak now.
Thanks, Greg. I appreciate that. So as Greg just introduced, this is the title of my talk. And just briefly, I'm going to this is the outline, so I'll give you a sense of where I'm going to go throughout the course of the evening. And you can follow along here so you always know where I am as we're moving along. I'm going to talk a little bit about infrastructure, and talk about climate change projections, that is how we know that the climate is changing, what we do know about what has occurred and what we expect to occur, and then talk about how we're going to try to use this information to build resilient infrastructure. So let's get started with what is infrastructure. Well, this, of course, I'm a civil engineer, so mostly these are dealing with civil systems, civil infrastructure systems. And we see right in the center of this diagram, we've got climate and civil systems, because in civil engineering, the climate impacts the environment is plays a vital role in engineering design. So what I'll really focus on today is mostly transportation, a little bit on buildings and water systems, and this is our impact on infrastructure, and then some of the work I'm doing with the province and Paganel and a few other groups towards infrastructure planning and community development. So I've heard it said that civil engineering is the second oldest profession, and this is, of course, Mesopotamia was really the first, where the origins of civilization, and there's a lot of scholars, what a lot of scholars call the hydraulic civilizations, that it was the hydraulic structures and irrigation systems that led to the centralized government, and really was the base of modern civilization. Of course, you can't spell civilization without civil. We're civil engineers. As I go through this now, I'm going to kind of give you some basic characteristics of infrastructure and how, to illustrate how really embedded infrastructure is in our lives when we not even notice. This is the Basilica Cistern. This is in Istanbul. This dates from Roman times. This is the Medusa's head, and I visited this area. It's really quite spectacular. So this is underground. This is underneath the main part of the city. Quite literally, this kind of illustrates how infrastructure is sunk into or inside of other structures, but not just literally structures, but other social arrangements and technologies. So it's part of our system. A lot of times when we think of civil infrastructure, we think of these great works of civil engineering. This is a quite beautiful cable stay bridge in France that's actually got it's the tallest bridge in the world. I think that the one tower is over 330 meters, or around 330 meters high. So it's quite a beautiful piece of engineering. But even so, to illustrate this point, this infrastructure goes well beyond any one single event or one single piece of infrastructure, because it incorporates and encompasses a system. The Absolute Dike in Holland. So this was built in the 30s, late 20s and early 30s, and then you can see this extends about 32 kilometers across. This is the North Sea to keep the seawater out, and this which was once a saltwater harbor is now primarily freshwater. But if anybody's ever been to Holland, you have a sense of what that area is like and how the culture goes in with their water structures. Holland and the Netherlands are really the most advanced in terms of civil engineering and hydraulic engineering, because their country is mostly below sea level. So one of the points about infrastructure is that we take it for granted. So as an outsider going to a place like Holland or any place else, you tend to encounter infrastructure as something that needs to be learned about. So as a new participant in the culture and a social organization has to acquire a naturalized familiarity with the infrastructure as they become members. So these, the CN Tower on the left is probably familiar in Toronto. This was, I think, finished in 1976. It was the tallest freestanding structure in the world until the Burj Khalifa was built, and I think that was in 2007 or 2008. I remember actually visiting the CN Tower in the late 70s, not long after it was built. That'll put the age on me. But again, the point here is they're structures, they're buildings. They're not reinvented or reassembled each time. They serve a task, and they invisibly support these tasks. You see the beauty of these structures, and yet they're doing something. So it goes beyond just these great works. Now we move to a little more local. This is the Confederation Bridge, which is the longest bridge that goes over ice-covered waters in the world. It's one of the great achievements of engineering in Canada. And this aspect of infrastructure might not fit precisely with the example of the Confederation Bridge, but it's important to keep in mind that the infrastructure shapes and is shaped by conventions of the community of practice. This includes other professional engineers as well as the society in general. So getting even more local, this is Kitty Beatty Lake Dam, and I'm sure a lot of you have seen this, maybe not thought much about it. This is the main part of the dam, which is often referred to as a weir to control flows, but the control of the structure is behind these concrete structures here, and this is looking downstream. I think a lot of folks, though, in this area don't even really notice it. You might drive by this area, you might drive through it, and the point is that infrastructure will become transparent. It fits into other infrastructures and tools in a standardized fashion. One of the other key aspects, and we look on this, of course, I don't need to explain where this is that infrastructure inherits the strengths and limitations of its base. One of the things when I first moved here almost 3 years ago now, driving through downtown St. John's was very difficult in certain areas until I learned actually that it wasn't until 1948 that everybody used to drive on the left here. So a lot of downtown St. John's was set up for driving on the left. So when you think about some of these intersections, it would make sense if that were the case. And it's kind of an illustration how we build infrastructure on what's already existing. And we only really notice it when it fails. So when working infrastructure fails, that's when it really becomes visible. And this is from the remnants of Mitch in 2016. This is in Norris Arm. And you can see that the main point here is we don't really notice that we're going over a piece of infrastructure until it's no longer there. This is the same storm, and this is in St. Albans. And one of the issues with infrastructure, another aspect of it, is that it's very layered, it's complex, and so it needs to be repaired in a modular fashion. So these changes require time, negotiation, and adjustment with other aspects of the system. This is stuff that's really important to keep in mind when we're talking about resilient infrastructure. When we're talking about, again, we're talking about systems and not just one piece of infrastructure when we talk about resilience. So why does it fail? Well, in the case, there are many reasons why infrastructure will fail. It could be the design flaws. But when it's not due to a certain design flaw, either the infrastructure is reaching the end of its life and it's deteriorated to the point where it would eventually fail, or it's going to, the conditions it's under go beyond what it was designed for. So this is a normal distribution, right? So this gives us our probability distribution. Everybody's familiar with the bell curve, I believe. So we've got our mean values, right? And then we got values below the mean and values above the mean. So this is for temperature. So this is an illustration of what average temperatures might look like for any given area you may be. But when we talk about design, we have to worry about the extremes. These are the things that we're going to design for. What's happening at the extreme ends of these distributions. So they're less likely to occur, but when they occur, they could have major impact. This is the same concept. This is the probability distribution for precipitation. So most precipitation is light, so there's a lot of light precipitation events, and then they decrease as they increase, so we have fewer and fewer heavy events. And of course, when we talk about design, in particular of drainage, of culverts, any kind of water infrastructure, same thing with transportation, with roads, we have to deal with the extremes. And this is where climate change is having an impact, is on these extremes, which are really, really important for design. So I'm going to this will be a little bit of a step back. I'm going to go over the climate change projections. This is where we get our information from. So some of the work I do, we have to start with what we know from the climate models. So I'm going to take a little step back, and now this is Fry Richardson. So he was a Quaker, and he was, during the First World War, during his spare time, he worked in a hospital unit, and he produced a 6-hour forecast, so just using a slide rule. So this was, again, I think around 1916, 1917. It took him 6 months to do this, so it wasn't a very practical exercise because his forecast wouldn't really do any good. Besides that, the forecast was completely wrong. But the thing was, he got the methods down. He had the basics correct. And so this was really the first forecast, and that's for weather. When we talk about climate, of course, today's forecast systems are full climate models. But when we talk about climate and climate change and climate projections, the climate system is very complex, and there's a lot of processes going on. What we want to focus on here is we have the solar inputs, we have our energy coming in, and then we've got re-radiation out, but with increased carbon dioxide concentrations, we're getting less re-radiation of heat out, so our atmosphere is warming up. But again, this is gives us an illustration of the complexity of the climate system. And as time has progressed and we've gotten better able at computing with greater computing power. So this diagram shows the performance. So this is the number of operations that a computer could perform per second. And so this is 1 and the number after it, after the E, is the number of zeros following it. So it's increased quite a bit from Leo. This was the first commercial computer available, to where we are about now, which is just orders of magnitude, 17 orders of magnitude greater. So this has allowed climate scientists to simulate these climate processes and the interactions in the climate much more clearly. So the way the global models work is that we have a grid. They create a grid that surrounds the entire globe, so it's of the complete and total atmosphere. And then these processes that I showed previously are simulated in here. And as computing power developed and got better, we were able to have a higher resolution model. So this is from the first assessment report. So this is the IPCC, the Intergovernmental Panel on Climate Change. And back when they first realized that the climate was potentially changing and going to change in the future, they put out this assessment report. And this 1990 was about halfway up that graph with computer power. And so our grid sizes were pretty large. So I was going to offer a loonie to anybody who can tell me where this is, but I forgot to bring it, so I can't offer that. So, but just for fun, if anybody, we got a quarter. If anybody can tell me what area of the world this is, and this is just, these are elevations, so the colors are the elevations. So this is our grid. It's 500 kilometers by 500 kilometers. Well, it's really hard to tell, right? And it's because the resolution is very, very coarse. Maybe you can start to tell now. So this is 1995, where we've got 250 kilometer grids. And again, keep in mind now, as the resolution increases, we're better able to capture the climate processes and simulate the climate. So that's Europe. And here we've got Iceland appearing. It appeared in the previous one. This is Greenland. So you can see as computing power increased And our grid size, the grid size of these models got smaller, then the ability to simulate the climate, the atmospheric processes, atmospheric circulation became much more advanced. So this is 2001, this is 2007. And one of the things I'll point out here when we move to the next slide, so each of so this is the third assessment report that SAR was the second, this is the third, this is the fourth assessment report, where now they're doing assessment report 4. So we're down 110 kilometer grids. And now the most recent one is about 90 kilometer grids, and then they run even smaller models or more higher resolution models at this one's at 30 kilometers. You can see how much this improves the representation of the world. And it's able to capture a lot more of those processes, the climate processes that impact climate. You also see that it's got a lot more detail on the ocean as well, so because ocean circulation is a vital part of this. So I'm going to show you some climate change projections for the province. The grid size on that model is 25 kilometers, so not too much different from this, but it gets a really good level of detail with these models. And then, of course, what I just showed you was just really the elevation. This gives you an illustration that we've got grids that go up into the upper atmosphere. It includes interaction with the ocean, and they simulate the ocean currents and the interaction of land. So as these models have progressed, and in particular as computing power has increased, we're able to capture and simulate these processes in much more detail. So this is Hurricane Sandy. So this occurred in October 2012. And so at this time, actually, this is when I was living in New Jersey at this time, and I'm not too far. So the eye of the storm came over Atlantic City, New Jersey, and I lived about 100 miles from Atlantic City inland, and we got the eye of the storm as well where I lived. But we had no wind, no rain, very little impact where I was inland and right near Philadelphia. However, along the coast, it was catastrophic damage, of course. But the reason why I showed it, so this was a model. This was forecast by the Hurricane Center in the U.S. And normally, so when we look at engineering design, when we are looking at what's happening, we're using our extremes, our data to design our infrastructure. We're using historical data, so it's stuff that's happened. This hurricane, when it came up the coast, was forecast to take a left turn. So it was forecast to come up the coast and then take a left turn into the U.S. around New Jersey, which is what happened. Never before in history, and it was never been observed before that a hurricane had done that. And it was just our simulation models, the numerical prediction models, which are fully global forecasts, predicted this turn. So my point is that if we rely on historical data and our climate is changing, then we would have never predicted this event. And the prediction saved a lot of lives because they knew it was coming. And this just gives us an illustration of how good these forecasting systems are, how good these models are. But again, this is a forecast, and of course our climate and weather aren't the same. So that Hurricane Sandy is a weather event. So we're not talking about weather, we're talking about climate. So quite simply, weather can be defined as the state of the atmosphere at some place and at some time. Whereas climate is the average of weather over some period of time. One of the ways to think about the difference is that if you think about the clothes in your closet represent the climate. What you're going to wear on a particular day depends on. So if you want to know what climate you're in, look at the clothes you have in your closet. And if you want to be prepared for the really different kind of day that the projections are telling us, you might want to put something else in your closet. But that's a key point. All right, so just kind of taking a closer look now at Newfoundland and Labrador. We've got several different climate zones. Based on temperature, we have 3 different climate zones, but these climate zones are also affected by not just temperature, also precipitation. So there's a temperature gradient as we move from north to south. It gets warmer, but we've got differences in rainfall along the coast of Labrador, Of course, along the Avalon and the southern part of Newfoundland, the mountains, the highlands create orographic effect, cause more precipitation. So there's a very complex, there's a very diverse climate in Newfoundland and Labrador throughout the province. So this creates kind of a unique challenge for the province, given that there's so many different types of climates, especially when we're making projections and designing infrastructure. We can't use the same type of information everywhere in the province. Okay, so what do we know? So let's talk about impacts. But before I do that, I just wanted to kind of reiterate the connection and the cause of the climate change being carbon dioxide. So this is our record of CO2 at Mauna Loa in Hawaii over the years from around 1960 through, well, this is right up to date, actually. So this shows how our CO2 concentrations have risen, and we've seen the accompanying rise in global temperatures as a result of this CO2 rise. And I'll show some of those impacts, especially in Labrador. And we look at the future when we're doing these projections. There's a number of different possible futures that are simulated for the models. So we look at so it's the emissions of CO2 and other greenhouse gases that are causing the change. And so in the worst case, these are going to be our CO2 concentrations. We're at just around 400 now, and as these increase, the effects of climate change are going to get larger and larger. So most of the results, actually all the results I'm showing you, are going to be for the worst case scenario, which is really the trajectory we're on now. And in particular, with the current political situation in the US, it doesn't look like it's going to get much better. So this is just a global view now. So this is our temperature. The scaling is just per degree of mean temperature. We don't worry about the details of that. The point is simply that we see where most of the warming is going to occur and has already occurred is in the Arctic regions. And this is in the more distant future. We have even larger increases. But again, you can make out some of the details here for where the increases are, and to a large extent, much greater in the Arctic region. So now we turn to what's happening in the province. So this represents the change in our average annual temperature from our climatic average for the past 30 years. So relative to our present condition, this is how much of a change we can expect in temperature. And all the information I present to you on change, that's what we're showing here. And this is brand new. This analysis was just completed 2 weeks ago. Joel Finnis, who's in Geography Department, climatologist in the Geography Department, had done the analysis, and I helped them with some aspects of it. But these are the newest results that are now available. So when we look at average temperature, we have a pretty good increase, a couple of 3, 4, 5 degrees, which is pretty significant. And we can see it's a little bit warmer up here. But again, that's average annual. We really see the differences is in the winter. So the winters are projected to get a lot warmer, and in particular in northern Labrador. And on the Avalon, we're not going to see as much of an increase in winter temperatures, but we're still going to be a little bit warmer in the winter. So this already has significant impacts. So these are images from Labrador. So this is some trail that in February 2010 had no snow on it in this area. And this is a landfast sea ice route, which is vital to transportation up there. So this has significant impacts and has already had significant impacts in Labrador. 2011 was actually one of the warmest winters on record. Those are the temperatures that are actually expected to recur more frequently in the next 20 or 30 years into the future. So this was a particularly warm winter, but it happened, and these are what the effects are going to be. These are some other images of Labrador, where we see these conditions again in 2011 that are more likely to be the case in the not too distant future. and how we have conditions typical of May occurring in February, and these water bodies that are used a lot of times, at least for transportation, are no longer frozen, can't be used. So the ice is part of the infrastructure up there that's being impacted. So again, these are impacts we've already seen, and it's just going to get worse as we move along. Not everything's going to be bad. So here's a potential good outcome, is a decrease in the number of heating degree days. So heating degree days simply are, the numbers are calculated based on the number of hours in a day that are above or below a certain temperature. In the case for heating degree days, it's below a certain temperature. So you can see there's going to be a greater decrease in heating degree days in northern Labrador than there is for us here in St. John's, which makes perfect sense. And just to give you kind of some context here, these are the around the average number of heating degree days each year for our region. This graph just shows really how energy use is directly related to the number of heating degree days. So this is going to be a positive impact where some of the heating bills and heating requirements will be reduced throughout the province. That could be offset by some of the increase in cooling degree days. So we'll need to run your air conditioner a little bit more when it comes to summertime. So there might be some of that benefit offset here. Some other possible benefits is there might be a reduce in frost-free days. There's expected reduction in frost-free days throughout the year. And in this case, our growing season is expected to be extended. So those are another potential positive impacts. But there's so many other different things here that I don't want to talk about the specifics of temperature change anymore, but I want to return to the distributions. So these are, this is one of the impacts with the climate change. So we've got our original temperature distribution. We're at our mean. When we have an increase in the mean, it shifts our entire distribution up. So our means are higher. We're going to have more hot weather, more record hot weather, and less cold weather in this particular case. And this is what we're likely to see in Labrador. In other cases where we might not see as much of a change in average temperature, we see an increase in the variance of the temperature. So when in fact the new climate will have a lot more record hot weather, but also could have a lot more record cold weather. So the climate change could impact both average temperatures and variance. And in this case, we get this is our new climate, where we have significantly more hot weather. And again, the extremes are what matter for design. Okay, so that's temperature. So now let's look at precipitation. So again, this is our annual precipitation. This is the change. So it represents an increase. And so this is measured in millimeters. So if our average precipitation in St. John's is about 1,300 millimeters, it doesn't seem like much of a change. And it's really, the total amount of precipitation isn't expected to change very much. But that doesn't really matter so much for us for designing an infrastructure. What matters are really the intensities. So how quickly the rain is falling is what really matters. And that's what we when we look at when we're designing, especially drainage infrastructure or culverts. It's those larger events, more intense rainfall events that cause some of the issues. So this is what we expect. Again, there's a change by season. So we see a lot more intensity in the winter. Now this higher intensity precipitation in the winter coupled with warmer temperatures could lead to significant flooding, because if we've got snow and we have rain occurring on snow where it's warmed up, these are where we have the really, really big flood events, or potential for really, really big flood events. This is spring and fall. We don't see as much of a change in the spring, but the fall we're expected more intense rainfall. The other important aspect is for those longer events that drop a lot of rainfall. So the damage that I showed you earlier, the failures of the culvert and the bridge, were because of the hurricanes, which were really 24-hour storms that dropped 200 millimeters of rainfall. And so this gives us an indication of those kind of events where we have more precipitation occurring over amount of time which can really have significant impact on infrastructure. So here's our precipitation curve, our probability curve for precipitation. So this represents the change where we've got our old climate and our new climate. And what we see is an increase in heavy precipitation. And this has also been observed as well. There's actually fewer small rainfall events, and there's more rainfall occurring in larger events. And this is what really is most the biggest changes and potential changes occurring with designing infrastructure are these heavy rainfall events. And so this is where we're really, really concerned. And these projections allow us to give us estimates of these that we use in design of infrastructure. Finally, I want to talk about sea level. So sea level rise this is what's occurring, and I'll go quickly through this. We can see the red line is the average, and it varies throughout the globe due to a variety of reasons. But we can see there's quite a bit around Newfoundland and Labrador, and that's got to do with mostly the melting of glaciers, and so the melting of the Greenland ice sheet, and the fact that Newfoundland is sinking a little bit. So the relative sea rise is greater along Newfoundland than it is in other parts of the world. So this is a couple images from Point Verde. Forgive me if I've said that wrong. I'm not sure if that's correct. But this is from 1995, and you can see as time progressed, as sea levels rise, they have more of an impact on the cliff. They start to undercut parts of the cliff, and you get coastal erosion. And so with sea level rise, you're going to see there's coastal erosion being a larger and larger problem throughout much of the province. Additionally, with sea level rise and an increase in the potential for big storms, we can see greater storm surge, which can cause quite a bit of damage. And this is from Placentia. I'm not sure when this is from, quite honestly, but it illustrates the impacts of storm surge that can be expected to get worse in the future. And I want to thank Melanie Irvin from the government of Newfoundland and Labrador sent me these slides to do a lot of work with coastal erosion. All right, so it's only going to get worse. And again, we're a hot spot, and this is a kind of a zoom in here where it shows that the most sea level rise really throughout the globe is expected to be right in our backyard. All right, so we talk about resilience and infrastructure. Basically, resilience is defined as the capacity for a system to recover after disturbances. So this, again, an infrastructure system, we think about, we can't really treat this as at one piece of infrastructure. So if a bridge fails, it's not, that failure affects the entire system. And so the resilience comes in with the community response and how infrastructure supports that community response. And this ties in closely with sustainability. So this is more of a long-term aspect and the capacity to preserve the system in the long run. So thinking back to some of the stuff I talked about at the start with infrastructure, when we think about building resilience into infrastructure, we're not just talking about one piece of infrastructure, although that's where the process starts. We're talking about the entire system, and because we're working from a base that already exists, we have to include and work with those types of issues as well. So it's a big challenge, and one that we're trying to meet. So I do want to quickly go over two different approaches to resilience and also sustainability, and that's mitigation and adaptation. So if we look at, this is our CO2 emissions line. So adaptation refers to dealing with the climate change that has occurred or we know will occur. So with climate change, we know we're on a trajectory for so much more climate change. We can't do anything about that. So we have to adapt to that. Mitigation involves cutting back on CO2 release so that we don't see that climate change. So mitigates the impacts of CO2, so we don't have to worry about that climate change. We stop it before it occurs. Pardon me. So a big part of mitigation comes in with the design of buildings. Now, a lot of this is from the architectural perspective, and there are aspects. There are a lot of engineers. There is certification for engineers, for structural engineers, for this aspect of building resilient and sustainable infrastructure. I really don't know that much. I do water resources, so I can't say too much about this. But again, a lot of this is on the design side and incorporates some of the engineering, but a lot of it is architectural. But when we talk about adaptation, when it comes to structures, so these are things again that I've just learned recently because I'm not a structural engineer, but any part of civil engineering, we have to worry about environmental impacts, what structural engineers call environmental loads. So with changes in climate, we could have changes in rainfall or changes in wind, so there are wind loads, which are really important for structural engineers. And when we talk about what's going on in our building and the difference between the inside and the outside, so there's air pressure and temperature differences that need to be taken into account. So these are the types of things that climate change impacts when it comes to structural design. Again, this is not my area, so I can't. There's not much more I can say about this aspect. So I do water, and when we talk about precipitation, so this shows us. So this is the kind of information. This doesn't show magnitudes, but the types of storms that we use to design drainage infrastructure are expected to increase by a pretty large amount as we move forward. And so when we're designing a piece of infrastructure that's going to have a life of 30, 40 years, if we look 30, 40 years into the future, if we were to use our historical data, we could not design for the types of events that are more likely to occur. So when we build resilience into our systems, this is the way we do it with the information we have. We have the projections, we look at the way the climate is going to be, and we use those as our design criteria. And this is just a simple example, but hopefully it'll avoid this type of situation because simply this is just most likely the effect of on a rainfall event that this culvert was not designed to handle because the event was probably larger than one that ever occurred before. And this was also, this was 2016, so from Mitch. And this is more recent, so I showed you that nor'easter when I showed you weather. I think this is the parts that hit Newfoundland. So this is out along the west coast where there's another culvert washout. So what we are doing, so I'm part of a project where it's called Building and Sustaining Infrastructure Resilience through Targeted Climate Adaptation Training for Professionals in Newfoundland and Labrador. And what this is, so what I've shown you is kind of work that I do as a civil engineer that then gets given to the engineers in practice doing the design. So engineers who are actually on the ground doing the work are not responsible for understanding all this and doing all this stuff. However, they need the results, and they need to know that climate's changing. So it's my job, with help of others, to create the new projections, to set up the new design criteria, and then we got to get it to professionals. So this is what this project does. It's a way that we're going out there, and a lot of the tools, a lot of the projections, the climate change projections are already there. One of the things, when I first came to Newfoundland and Labrador, I was very, very impressed with how much they've already done with climate change. Very much ahead of the game than any other of the Atlantic provinces. But we're working with the government, the Climate Change Office. We do work with Paganel and the municipalities, Newfoundland and Labrador, and Engineers Canada on this project. And this is funded by Natural Resources Canada, which is a national, from a national perspective, there's a move for building resilience and adaptability into infrastructure. So this is an exciting project. And we're hoping and I'm not trying to put them on the spot, but we're hoping to integrate a lot of this, some of this into our curriculum as well. One of the connections with MUN is that we know we've got a lot of the expertise, but we also want to train those new and emerging professionals with this material coming out, so it just becomes part of common practice. That part of infrastructure, again, that it gets built in without. Ultimately, you don't notice it, but it's there. And we need to start with the training. And the last thing I'm going to leave you with here. This is the website that the government has, and if you haven't seen it, I really highly recommend looking at it because it's got great information. It talks really on all levels as to what's going on. There's links to technical data. There's all kinds of important information on this about the climate change excuse me, plan of the province and other aspects that work the province is doing, which is really a lot of great work. They're doing a lot of great work over there. So, with that, I did.
Thank you very much, Joe. That was a very interesting talk, to say the least. I'm sure there are many questions in the audience, so I'd like to just ask if you have any questions, please raise your hand. I will come along, either I or Jackie, with the microphone that you can ask and we can all hear.
Do you have any examples of some really innovative stuff that's being done in this province or elsewhere in terms of addressing these issues around infrastructure?
Not on hand, but yes, there's one of the impeti. I don't know what the proper use is. One of the things driving that project that we're working on was the fact that the province had all this great information on climate change and on especially like floodplain mapping and other types of information that could be used for design, but it was not being used. People weren't aware of it. So that was one of the things going on. So in terms of within Newfoundland, yes, there are some examples. I couldn't tell you right offhand, but a lot of the more interesting stuff is occurring in Ontario. And a lot of stuff in BC that I've seen in Canada and in the U.S. as well. So there are examples, and I can certainly point you in that direction to give you more specifics if you're interested.
I can comment on that question a bit. Okay. I'm involved in dam safety assessments, and it's been an ongoing program across the country. Existing spillways, existing systems are being revisited to see if their design assumptions meet current standards. And this includes developments in the watershed, but also climate change is a factor that increasingly is being considered, both in Newfoundland and elsewhere, by the way. My question to you regards whether you've looked at the hydrometric record in Newfoundland for evidence of climate change, and what have you found?
I haven't looked at it in detail. I have done, actually as part of my class that I teach, I've had students do some trend analysis to see if there are any trends in stream flows anywhere in the province. We pick a variety of places, and it's not consistent, and so a lot of places are seeing increases in stream flow. Some places are seeing decreases. It's hard to pick out trends for regulated rivers because you see a regulated flow, you don't know what kind of trends you're pulling out. I haven't done any systematic analysis, but I have looked at some areas, and it varies throughout from what I've seen.
I've been involved in some similar analysis from Northwest Territories, where climate change is happening in a more intense fashion.
Yeah.
We did find consistent trends in warming, which from our limited analysis confirmed information that's been published. We didn't find any trends regarding precipitation, but we did find increased variability with annual floods, examining the flood behavior of a couple of pristine rivers. And this confirms an observation generally held that part of the result of climate change is more intense storms, larger storms happening more often.
Yeah, and I also seen that in the record, in the work that Joel Finnis has done with the intensity, duration, frequency curves shows definite increases from the present. We're actually one of my grad students is we're doing we're looking at really design storms and some of the distributions, rainfall distributions throughout the record. Now we're working on a paper now, looking at some of the precipitation in particular to be coupled with the IDF stuff. So we're only halfway through. We haven't done all the analysis yet. We are working on something that should tell us a little more throughout the province. So, and we got a lot of different climate zones in the province. So it'll be interesting to see what happens, see what we find.
So hand over here.
We looked at the climate change impacts. We looked at temperature, precipitation, and sea level. Just wondering how wind plays into that.
Yeah.
It seems to be, I guess through conversations, higher intensity, wind events, more frequent. So just wonder if that's being looked at in studies.
Again, I'm not a climatologist, and I've talked with Joel Finnis, who is a climatologist, about the wind issue. He said he's told me that he hasn't been able to find anything in the record. What I do know, what I have seen with the climate projections is well, let me say this, that the surface winds are very difficult for climate models to project because there's so many interactions at smaller scales. But the large scale, especially the kind of the not upper atmosphere, but just right above cloud level, the projection so increases in intensity right along, going right across the North Atlantic, really right over Newfoundland. So it seems likely that there will be an impact. As to what it will be, I certainly don't know enough to answer what it will be. I have heard that people who pay attention to it have noticed differences. But again, from what I'm talking to Joel, he said he hasn't been able to find or confirm anything with data, but there's very little data available as well. That's one of the big problems is that we need surface data, and it's just not there to really say what's happening.
Hey, hello, this is a very nice speech I have experienced here, and thank you for your fresh ideas for here. I'm also an engineering student, as I don't know, for the instruction projects, there will always be billions of dollars for a project to precise. So my question is in the future, is there any possible for us to keep the balance of the economic development with this virtue and to see if we could help for change the climate? Especially now we know climate change is not only a regional problems, it's concerned with the global warming and with the whole world green gas release to make this climate change. So I want to know, is there some possible in the future we can combine it with our economic development with this infrastructure projects? Thank you.
That's beyond my capacity to really answer. I can say that that's a trade-off because I mean ideally you can design and over-design for potential climate change, but the cost becomes prohibitive. So there's a feedback between cost and risk. So when we talk about climate change and what's going to happen in the future, we're talking about changes in risk. So the risk goes up, and so there's a balance, and there are people. I don't know how to do it. I've seen it. I know there's work being done, and engineers do this kind of analyses where they look at the trade-off between the cost of building climate resilient or climate resistant infrastructure and the economic costs. So there's got to be some. I know there are. I'm sure there's people doing work on this but that's as much as I can say on it. So.
Okay, that question was one that was asked of me today when I told somebody I was coming here tonight. In other words, it was asked, can we afford it? So I guess that relates to the question she's asking over there, which is a perfect question. Mine relates to the list of partners that you had on the board there in terms of who's involved in the project.
Yeah.
And only one provincial government department was listed there, the Environment Department. And as a matter of fact, as you know, the Public Works and Transportation Department and the Municipal Affairs Departments, they are the two major infrastructure departments in this province. How are they involved in this, and are they reacting positively to this? Are they putting plans in place, putting changes in place to their regulations and their criteria for design and so on to deal with this? Just if you can comment on that. If you can't, I understand that you can. But
yeah, I'm
just wondering how because they are the two major players in this province. Thank you.
Yeah, like I said, I can't. There's not much. I don't know enough to say what's actually going on there. But from what I've seen, there seems to be a lot of they're part of it because a lot, like when we had our workshop, we had a lot of folks from those departments at our workshop. So they're aware and they seem, from my perspective, from what I know, they seem to be on board. But that's just from my limited experience with what's happening there.
In your work, there's various modes of failure.
Mm-hmm.
You talked about risk and the cost of building things to prevent them from failing can sometimes be out of reach.
Yeah.
So are there thoughts in these processes of saying, well, I can design it to a certain level, and that's reasonable to do, but beyond that, it's going to fail.
Yeah.
And are there thoughts of saying, okay, maybe I can't design it to the ultimate, but I should look at the mode of failure?
Yeah, absolutely. And that's one way of adapting, of building a plan. If you know that the risk is increased for failure and you're limited by cost, you build in planning and contingencies for when it does fail. And it would directly increase the resilience of your system because you put things in place to, if whatever the piece of infrastructure is, you have things ready to go, and in particular in the form of planning. So that is one of the approaches to it when the money isn't there. So it's not just about the asset, it's about the whole system. So that would be a way to build it into the entire system.
Joel, I just wondered that there's a life cycle associated with infrastructure, right?
Yeah.
So we build it, and then it lasts for so long, and then we need to renew it.
Yep.
And so do we build? I guess that so there's that cycle. There's also what we're seeing that in climate change is going to increase, and of course you never showed it, but there's uncertainties associated with a lot of these climate projections as well, particularly as we go farther and farther out. Well, you did show those number of scenarios, and so we don't know where we're going to go. So do we maybe we should design on shorter life cycles, and because infrastructure has a natural has natural adaptability built in, because we need to continually renew it. And I wonder, do we take those into consideration when when we're designing our infrastructure to be climate tolerant.
Yeah, and that again, that's another adaptation approach. And it's not necessarily to shorter design life, but I don't know if anybody's aware of the Thames River project in the UK. So that is designed to be redesigned every so often, every 20, 30 years, depending on the observed climate change and new projections. So there's, again, contingencies built in so that, okay, we're designing to this level, but you might leave in areas for increasing capacity or whatever the case may be. Again, it becomes part of a planning process where you know, and again, it's based on economics as well, how much money you have, and but again, the Thames River project is working that way. It's designed to be redesigned every 10, 20, 30 years as need be, and I think they have a funding mechanism as well for those future designs in there. So again, that's another approach to do it. And as far as designing, you know, for shorter life, you know, I don't, you know, I think it's kind of one and the same when you look at it that way, right? So, yeah. Yeah. Yeah, exactly.
We have time for one more question.
Hello. Demographically, Newfoundland is known for having a fairly large number of fairly small communities. And, for example, St. John's, budget scaling to population, everyone pays a certain amount of taxes. St. John's is going to be more prepared than a place like Marystown. A place like Marystown is going to be more prepared to change its infrastructure than a small community with less than 100 people. What suggestions would you have for people living, for how to change infrastructure in these small towns with 2 and 3 digits to their population?
Well, I can tell you that the municipalities in Newfoundland and Labrador is working on with the asset management program, which has a lot to do with resilience and things like that. And they're reaching out and representing some of the smaller communities for that very reason. You know, I don't know, quite honestly. I mean, that's one of the things, again, that the project that we're working on is also designed to get feedback so that we can kind of answer that question, because we don't know really what to do about a lot of these communities. There's not money, and so you got to work with them. But again, we're part of this project is to get that kind of input, because our project is not we're telling everybody what they need to do. We're kind of saying, this is what we have, what else do you need, how else can we work this out? So again, it's that community of practice, and it's also it's this whole social and community process as well. So because infrastructure is everywhere. Yeah.
Okay. Maybe just one more. I have one. So, Joe, I found the results very interesting on the climate projections in the future, and they all really kind of made sense in terms of where things are going. But there were two that really I found quite surprising. So one was highest sea level rise in the world in Newfoundland and Labrador. And the other one that I found surprising was the really small amount of precipitation change. So I think it was like 0.3 millimeters on a total yearly amount of 1,400. So I guess my question is, how good do you think these climate change models are in their predictions?
Well, I think the sea level is going to be good. The precipitation, the models seem to do relatively well with average precipitation, because it's about how much water the atmosphere can hold, and as temperatures increase, it can hold more water, you can get more rainfall. And most of the differences are seasonal, you know, so there's a different distribution. That being said, precipitation, there's a little more uncertainty with precipitation because the precipitation, the processes that impact precipitation are smaller scales than a lot of these models can capture very well. So from my perspective, I'm confident that we're going to see these increases, but the magnitudes might be more or less, you know. So it's like when I'm looking at, and again, that's what we do when we create these new design criteria. We look at the uncertainty as well. And some of these rainfall, there's more uncertainty with rainfall than with sea level. Sea level is much easier to project and predict than precip.
Okay, well, Dr. Dario, this has been a very, very interesting presentation with a lot of information that, you know, just has really, I think, changed our perspectives and made us appreciate the importance of this area of study on our future infrastructure. So I want to thank you very much for an excellent presentation and also give you a small token of appreciation on behalf of the faculty. So let's give Dr. Dario another round of applause. Thank you.
Well done. Thank you. Appreciate it. Appreciate it. Thank you.
Okay, at this point, I'd like to welcome Jeff Emberley up to say a few words on behalf of Paganel.
Thank you very much, Dr. Natter. And professional engineers and geoscientists, Newfoundland and Labrador, I represent them. We're very happy to be part of this type of event. As I can see, many people here I know, professional engineers and geoscientists, Newfoundland and Labrador, we're a regulatory authority where we regulate the practice of engineering and geoscience, primarily through regulating the licensure of engineers and geoscientists, and that's a very important part of what we do. And to be part of this really reinforces that whole framework of being able to reach out to people, especially the people we license, but the general public in total, and to be part of these particular issues. When we look at climate change and things like that, that's a very important part of what a lot of engineers do. Geoscientists probably have a better appreciation for it because they have a much larger time frame. And when I talk to geoscientists, I get the feeling that you know, climate change has always been with us, for more or for less, and what we're seeing these days is for more than what we've seen in the past, and probably caused by people in large measure, but by other factors as well. So that's really an important viewpoint that the geoscientists bring to us. But looking back at the engineers are an integral part of the design of a lot of our infrastructure. And what these people do, it's very important that they be aware of these things. And engineers in general design to codes and standards. And that's a lot of what they do. And these standards have been developed over time. And when you say over time, that means backward looking in large measure. So a lot of the codes and standards that we have been developed based on past weather, past climate, I guess is the proper term. And you know, we're looking to work with groups like Dr. Dario's to change those. We work with our National Association, Engineers Canada, and they've been quite innovative in this area as well on an international scale. But looking back to codes and standards, we recently put out a publication to all the people that we license, and we said that designing to existing codes and standards is not always enough. And that especially in today's world with climate change, that you have to not just design to those codes and standards, you have to look around you and make sure that you're really aware of what's happening. And so models like this will eventually affect codes and standards, but until they do in large measure, you know, you have to be careful. So that's an important message that we're passing on to the people that we license. But in general, I'd really like to thank you for your presentation, and it's been good to work with that group that you had up there. It's really an important part of our working with the community to do better, and thank you again, Dr. Dario. One important point, there's refreshments served outside, and stay around and chat.